Hello students, welcome back. Let's go to section 5. We are still in Cauchy-Euler equations, but instead of staying in second order, let's go to higher order. Computation will be a little bit harder, but not too bad. Not bad at all, actually, compared with some of the other things we are going to be doing. Anyway, here's the general circumstance, general situation. T to the nth power times nth derivative, n minus first power times n minus first derivative, and so on. Now the change of variable method, we can use this change of variable. T is equal to e to the x, consequently x is equal to log of x. So if I said y and z are the same, where same function, where y is expressed in terms of t, z is same quantity expressed in terms of x, then we can take the derivatives. By chain rule, we have this dx dt popping up, which is 1 over t. X is log of t, so we get that. And then from here, that is here, take the derivative once more, and by product rule, we have derivative of the first function, second function, first function, the derivative of second function. And when you take the derivative of the first function, chain rule, we have dx dt, so we have another 1 over t. Here, taking the derivative of 1 over t, we have 1 over t squared comes out. So that's 1 over t squared is common. So we get this. Keep going. From here, take the derivative again. We have third derivative. And by product rule, we have the derivative of the left-hand side and then right-hand side. Left-hand side times the derivative of the right-hand side. When you take the derivative of the right-hand side, we have t to the third power in the denominator. And when you take the derivative of here, we have 1 over t coming from that chain rule, you see. X is log of t, so taking the derivative, we have 1 over t. So either way, I'm getting 1 over t to the third power. Do it again, the same thing, t to the third power is there before. I get this 1 over t from the chain rule. Well, here we have something over t to the fourth power because of this derivative computation. So in any case, we have t to the fourth power. Do it again, same deal. Therefore, this change of variable is actually valid. So the original equation becomes like this. Some polynomial expression of this derivative of z. So some d to the nth derivative and some n minus first and then something. And this one goes up to n minus first derivative and so on and so forth. So in the end, complicated they may be, but we have to have n derivatives. So we get order n, and then all the coefficients are all jumbled up, you see, and these are polynomial expressions of derivatives, so things are complicated. But if you actually sit down and do your computation, then these are supposed to be all constants. So theoretically, at least, we can take the characteristic polynomial, factor it, again, theoretically, and then you can go ahead with the usual method of Laplace transform, R over Q, and then take the decomposition by partial fraction, again, theoretically, and then take Laplace inversion. Yeah, that's basically it. We have x to the j power. J is going from 0 to m minus 1, where m is multiplicity. And this x to the j power, that'll translate into log of t to the j power. And then exponential part is t to the characteristic value, t to the lambda power. And that's the general form. Is anybody using this general form? Actually, nobody does that. Nobody will actually even use the change of variable method, to tell the truth. It's useful because it established theoretically. Substitution method, okay, if you do that, t to the s power and take those derivative, arbitrary derivative, okay, and put those back into the original ODE, and nth derivative and s minus n power. So again, cancellation. So t to the s power is always common. What's left is gonna be a polynomial of s, and it has degree n because over here we have n factors multiplied. So we have s to the nth power times something. So you get a certain polynomial here, and as a matter of fact, I better change all those characters here because characters will be changed accordingly. They are not going to be the same characters that we started off with. And then we have the characteristic polynomial here, and the answer is the same as before. T to the lambda part, alright, and then log to the certain power. And we begin with, of course, 0 power, so early on, if you have just single root, then log doesn't appear. For double root, we have times log, but then again, for higher order, we can consider triple logs and so on, triple root and so on. So you may have log squares and higher as well. Those are theories, and let's go to example problem. Okay, alright, let's solve this. It's an Euler equation. Does everybody see? Third power times third derivative, second power, second derivative, first power, first derivative, and so on. Here this is again Cauchy Euler equation, fourth power times fourth derivative, third power times third derivative, and so on. Alright, do you want to try on your own? Maybe you can stop this playback and go ahead. Let's go with substitution. Change a variable, I could show you, but the computation, oh my goodness. Substitution method, okay. T to the s power, and then take your derivative of the third derivative and then plug those in. Back to the original equation. And then you have to have t to the s power common. Otherwise something is wrong. So factor t to the s power out, and we get a cubic equation of s in there. Just be careful and expand them all. We get that. And again, be careful and simplify. We get that. And factoring this one back is not too bad. You can easily use factor by grouping. So group these two together. S squared is common, so s squared and s minus 1. And those two s minus 1. S minus 1 is common, so factor. And then in the end, that's what we get. So we get t to the s power is 0, so that gives you the singular solution. Y is always equal to 0. You see, y is t to the s power. It always shows up. And how about the s values, the characteristic values? We have -1 and +1, and +1 is double root. Conclusion, double root comes with log of t. Algebraically, a little bit more factorization, yeah, but this is not really too difficult. Now, I would regard this kind of computation as pretty normal, or actually on simpler side. How about the next problem here? This one, I think you'll have to use computer algebra system to factor this. Ready? Okay, here we go. Substitution. T to the s power, first derivative, second derivative, third derivative, and the fourth derivative. Oh my goodness. Plug all this in, and we have this formal expression. Okay, so far so good. T to the s power is always common, right? Fourth power minus 4, third power minus 3, they will cancel out, and t to the s power is common. What's left is inside. And simplifying all that, well, that's not a fun thing to do, so I cheated. I use Mathematica command. I copied and paste this part, and I ask Mathematica to expand this. So that's how I get this quadratic polynomial here. But then again, expanding is not that bad. Factoring is bad. How do you factor this? Yes, you can do factor theorem, but then again, oh come on, that's elementary but really tedious. Nowadays, proficiency in a computer algebra system is a part of legitimate mathematics skill. And I want you to use it, especially in this course, in Math 3410. If you cannot use computer algebra system, you're doomed. You'll have to do all this computation with your paper and pencil. You can't do it. I mean, you can, but, you see what I mean. So, use factor command to factor it. So I got s minus 1, s minus 2, and then this quadratic irreducible. That's what I got. And then this quadratic irreducible, I can simplify a little bit further in complete square. So, do we have those characteristic values? S is 1, good. S is 2, another 1. And then S is 1 plus square root of 2i, 1 minus square root of 2i. They're all coming from here. Or, of course, you can use quadratic formula here to find out the roots. Maybe that's easier. Yeah, you didn't need this complete square here. You could have gone directly from here to there. Okay, alright. T to the s power is 0. That gives you a singular solution. Y is constantly equal to 0. That always comes. And then s is 1, 2. They're going to be t power, second power. No problem there. Now how about the complex part? T to the 1 power, because this is 1. And then cosine, sine, square root of 2 times log. So I use some computer algebra system to factor, but otherwise pretty straightforward actually. You see, if you have up to here, if somebody does this for you, then getting this solution here in the end should not be too much of a problem. We have complex roots, so we have t to some power, cosine, sine. By the way, this is checking process through Mathematica. Left hand side minus right hand side. No, excuse me, there's no right hand side here, equal to 0, okay. If you somehow want to use change of variable method, I did the computation here. I skipped several steps in between, but still it became really this long. I don't recommend it. Change of variable method is good justification on how those log of t is popping up, but that's where it stops. Actual computation, the substitution method is superior, at least in my opinion. Okay, we are done with Cauchy-Euler equations, second order and also higher order as well. What we didn't do yet is the general solution theorem. We did prove the first half of it. The linearly independent solutions, y1 through yn exist, okay? But once you find those, then those are the general solutions. The linear combination yields a general solution. That's something we didn't prove yet, and we are going to do that in an optional video. It goes really deep.